So I don't have to do all this.
Oh, nice.
Midterm project.
There you go. There you go. It's okay. You can say I extended the deadline till end of spring break. After that.
Dr. Tron, can you hear me?
Oh, hello, Ivan. Did you say something?
Yeah, hello.
Hey.
Can you hear me?
Yep, I can hear you.
Okay, sounds good.
All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. It's our last class session before spring break. How's everyone doing today? Doing good?
Good.
With only one other person here in the class today. All right. So the plan today, we're going to finish up our lecture notes on non-linearities. I don't have that much more to cover. And actually, a lot of it is kind of repeat of what we talked about before in terms of material properties. And so I expect that we're going to finish pretty early today. We should have around either 30 to 45 minutes left today. And so what I wanted to do after that is to leave time to work on the project. Okay. And so if you're here, of course, it's easier for me to kind of look at your project, but I'll do my best to look over Zoom as well. Okay. All right. That is it for my announcements. Remember, the midterm project is due this upcoming Monday. So it's crunch time for that. So we have 5 more days for the project. And so if you have questions on the project, if you're running into issues on the project, just shoot me an email, let me know. Or if you have them today, I'd be happy to take a look as well. Okay. Okay. I think that's all my announcements. Are there any questions I can answer before we get started for today?
I have one if no one inside the classroom has any.
Sure. Go ahead, Ivan.
So does that imply that lecture is gonna end early?
Yes. I mean, the amount of content that I have for the lecture today is probably only going to take 30, 45 minutes. And then the rest of the time is going to be for project workshop, basically. So yeah, if you don't have questions on the project or if you don't want me to look at anything, then you can leave after that. Yeah.
But we can still email you if we have any questions, right?
Of course, yeah.
Oh,
and
sounds
so
good.
yeah, my email is open. I have office hours tomorrow as well. If you
Perfect.
want to make an appointment to meet outside of office hours over Zoom, just let me know as well. So I'm going to try to be as available as I can up until.
Thank you, Dr. Chan.
Yeah. Mm-hmm. Okay. Any other questions before we get started? Okay. All right. So let's go ahead and pick up where we left off on Monday. So on Monday, we were in the middle of talking about non-linearities in FEA, right? So we talked about what that means, what it means for a basically to have nonlinear behavior in your FEA solution. And we are in the middle of talking about kind of the main sources of that nonlinearity. Okay. We left off specifically talking about the second source of nonlinearity, which is topology. Okay. Okay. And so by topology nonlinearities, what we're looking at is just nonlinear behavior that results between the interactions of different parts. Okay. And so on Monday, the last thing that we talked about was all the different types of contacts you can have, all the way from bonded to no separation to rough to frictional, and there's one more, and frictionless. Okay. So today, I want to kind of build off that. And in fact, the last thing that we were talking about was specifically, how does ANSYS enforce no penetration? Because when you have two parts that are touching each other, no matter what type of contact that you describe there, whether it's bonded or frictionless, no matter what, two parts cannot, phase into each other. They cannot, penetrate each other. And so there's different methods that ANSYS uses to apply this. Okay. And they all have very slightly different behavior, and it may result in slightly different results as well. Okay. But first, the one thing I want to talk about is that when you define a contact between two different parts of a simulation, maybe something you've noticed already from activities 3 and 4 is that you have to define one thing as the contact and the other as the target. Okay. And so, you may be wondering, what's the difference between these two, and does it matter, right? Because at the end of the day, you're defining a contact between two parts or two regions of two parts in your simulation. And so why did they give it different names? And so what does it actually matter? So it does actually matter, okay? And so in general, the way that ANSYS defined these, and these have to do with kind of this no penetration condition, usually you want to set your larger region to be the target and the smaller region to be the contact. Okay? If they're roughly the same size, then it doesn't really matter. But oftentimes you're gonna have one region that's bigger than the other, and you set that to be the target. So for example, in activity 4, when you were connecting the beams to the road, right, there was one part where you had, we had those 7 connecting beams on the bottom of the bridge, and you were connecting them to the road, right? And so we had our road, that looks something like this. And we had all of our beams on the bottom. Okay. Imagine there's 7 of them. And so in this particular case, the road is a much bigger surface than all of the beams. Okay. And so if you look back, and probably most of you kind of did this by accident, without really thinking about it. If you look at the contact between the beams and the road is the one that's set as the target, and the beams are the ones that set as the contact. And so one nice feature in ANSYS, and some of you may have noticed this already, is that if you define it the other way, right? And so let's say that you define your target and your contact, and you set your beams as the target, ANSYS will let you know, and so it'll say that we think that it should be the other way around. But there's kind of a very easy button to switch target and contact. Okay, so I wanted to give a little bit of context today about kind of why this matters, because it matters in terms of how ANSYS enforces no penetration. Okay. Okay. So there's actually, just like many things in ANSYS, there are several different methods to do this. Okay. The most common one is called the multi-point constraint, or MPC. Okay. So this is only available for the linear contacts. This is for bonded and no separation. Okay. And so what the multi-point constraint does is that it actually adds additional equations for the finite element to solve. And those additional equations add constraints to make sure that the surface motions are coupled. Okay? So this is kind of the most rigid way to satisfy no penetration. So you basically add additional equations to make it so that those two nodes kind of move together, or the nodes that are in contact that they move together. Okay. So if you're working with a multi-point constraint, you're basically guaranteed. You're guaranteed not only is there going to be no penetration, but you're guaranteed that those surfaces are also going to be also locked together. Okay. Okay. Kind of the similarities between those two. So because it's for bonded and no separation, is the fact that you have no normal motion. Right? So you have no normal motion of the object that's normal to the surface, right? And so you can kind of add this additional constraint because you're not getting any separation anyway. And so if there's no separation, then there should be no motion in the other direction, which is penetration as well. Okay. So that works the best. And so for all the activities we've done so far, we've basically utilized the multi-point constraint kind of without us realizing. Okay, and so all the other methods here are going to be more for the other methods. And so for the other contact types that allow separation, you need to use a different method to ensure that you don't have any penetration. And so the first method, the most common one, is called pure penalty. Okay, and so what this does is that it kind of indirectly specifies no penetration by applying a spring force. Okay. So the magnitude of the force depends on how much you're penetrating by, and it's also modulated by kind of a spring constant. Okay. I call it a spring force because obviously there's no actual spring there, but it's kind of a way for the for the simulation to basically, if you have any nodes that penetrate in, to kick it out. Okay. And so another way you can think of this is that this adds additional loads to your model if you do have a situation where your parts are are penetrating into each other. Okay. So it looks like this. And so I'm going to use an example. Let's say we have a target surface that's a square. We have another part that's penetrating into it. Okay. And so just like we said last time, this kind of overlapping is bad. Okay? But if we measure the amount of overlap, okay, and so the amount that this part is penetrating in, we'll call that x sub n. Okay. And so under pure penalty, ANTHUS is going to automatically apply another load to your structure. So we'll call it F sub n is equal to Kn xn. Okay. Where that F sub n is going to be applied basically like this. Okay. And so whenever you have a node that's kind of creeping into or phasing into another part, ANSYS will automatically apply another load there to kick it out. Okay? And the idea behind pure penalty is that you're going to select this value of Kn to be very high. It's you. So that even with just a slight amount of phasing into, which even with just a slight amount of penetration, you get a large amount of force that kicks that node out. Okay, so this is called a penalty method, and this is not the only. You may have heard of penalty methods from another course, and so this is kind of a whole branch or a whole kind of brand of different methods. This is just one way that it's applied in finite elements. Okay. And if you're curious about what this Kn parameter is called, this is something that you can actually control as well. And so this is called the normal stiffness. Okay. So the benefits of this is that it's a very natural thing because applying loads onto a finite element simulation is something that kind of already naturally happens. And so adding additional forces doesn't fundamentally change kind of the nature of the equations. Okay. Of course, the downside to this is that because it's not a direct specification, it's not an explicit specification, you could still have some degree of penetration, especially if you have a situation that's applying a large amount of force normal to the surface, right? So let's say you have like kind of an external load that's being applied this way, and it's very large. Right? If you have a very large external force being applied onto that surface, you're going to get some penetration because the penalty force is not going to be enough usually to push that out. You're probably going to reach equilibrium probably somewhere around here. Okay, so you might have a small degree of penetration. A lot of times, maybe that's not the biggest. It's not a huge deal if you have just a little bit of penetration. But if you're working with a very precise kind of situation, maybe like an aerospace application, that might be something that you might have to fix. And so you might have to either bump up the normal stiffness or you might have to do something else. Okay. One word of caution. So for the normal stiffness, so normally it is a value that's very high, and normally you want this normal stiffness to be very high because you want to enforce this no penetration. But you have to be careful. And so if you make Kn too high, it'll make your simulation much more difficult to converge. You want to be careful. And so, if I would just go with the default value first. And so, usually ANSYS does a pretty good job with the pure penalty, giving you a default value. But if you're still seeing some penetration that's not satisfactory to you, you can try bumping this up a little bit to see if that improves it. Okay. Or maybe you're not having any issues with penetration at all, and you want to improve the convergence of your simulation. Maybe you take it down as well. So that can also be a consideration. All right. Any questions on this? Okay. All right. And so another method, and this will be the last one that we go over, is called normal Lagrange. And so the idea behind normal Lagrange is it's very similar to pure penalty, where the way that you're going to essentially the way that you're enforcing no penetrations, you're going to be applying a force in the normal direction. Okay. But instead of having this normal force be proportional to the amount of penetration, the way normal Lagrange works is that it adds an additional degree of freedom. So basically, this is going to be another thing that ANSYS solves for in the simulation. Okay? And so the idea behind this is that you kind of make use of the fact that you're going to be solving a large system of equations anyway. And so if you solve this system and you add this additional degree of freedom, you can solve for it in a way that you don't get any penetration. Okay? And so this lambda right here, this is called the Lagrange multiplier. And the way that it's actually coded, the way that it's actually applied is that it's applied as a contact pressure. Okay. So there are some situations where normal Lagrange can work better. In fact, most situations it can work better because it's something that you directly solve for. The downside of normal Lagrange is that it does, because you're solving for more unknowns, you're solving for more variables, it can add to your computation time. Any questions on these? All right, so those are the three, I would say, three main methods. Okay. There's also another interesting setting. So this is not an additional method, but this is kind of a subsetting of these three, mostly for pure penalty and normal Lagrange. And that's this idea of a pinball region. Kind of has a funny name. So normally, if you have a pure penalty or you have a normal Lagrange method, usually those forces don't actually apply unless your node starts penetrating into the surface. Okay. But sometimes, there might be situations where you want to start applying that ejection force early. And so, when the two parts start to come close together, maybe that's when you start to think about applying your ejection force. Okay. And so modifying the pinball region. And so the way it works is that your pinball region, it's a spherical region. And so it has a radius that's defined by the user. So the idea with the pinball region is that if an offending node, and so a node maybe from a contact enters that pinball region, then you can start to apply the ejection force. All right, so this is useful for, maybe those pure penalty cases where you have a large amount of external force that's pushing the parts together. Maybe you apply a pinball region to apply that ejection force early so that they find some kind of equilibrium where the two parts don't penetrate each other and they just are just kind of sitting on the surface. Okay, so they're just contacting as they should be. This is a fairly advanced thing, and so this is for cases where you want to enforce this contact or no penetration condition very exactly. And so if you have a very precise application where those, a lot of times, even with the pure penalty or normal Lagrange, the amount of penetration you'll get will be probably on the order of like sub-millimeters or something like that. If that's not significant to your simulation, I would say don't worry about the pinball region. But if you are working with an application where those sub-millimeters are significant, then this is something that you might look into to make it just a little bit more precise. But it is. I played around with it a little bit. It is pretty finicky, so it's hard to get kind of really good unless you kind of practice it a lot and kind of really know what you're doing. All right, any questions on this? Okay, all right. So very quickly, let's go over nonlinear materials. We've already talked a lot about material properties, so there's not really much for me to say here, but I do want to kind of expand on a couple points that we didn't really expand upon before. And so when I talk about nonlinear materials, these are materials whose stress-strain relationship is not linear. So there are three kind of main material models, or I say three main material modes that we've talked about in this class. One that we've used pretty much exclusively, and then the other two are kind of the nonlinear. And so we have linear elasticity. That's kind of the one that we've been using pretty much exclusively in this class. Right. Next, we have plasticity. So we've talked about plasticity a couple of times before in this class. And so that's usually kind of what most people consider as kind of the extension of linear elasticity. Okay. And so if you have large deformations, and so the amount of strain that you have in your structure is very large, oftentimes the first thing people think of is plastic behavior. Okay. And the last one, which we haven't touched on too much, which is hyperelasticity. Okay. Okay. And so all of these are what I consider to be material models. Material models, when people say that, a material model is nothing more than a mathematical formulation for how stress and strain are related, which can be modulated by material parameters. One thing that we haven't covered, when we talk about material models yet, is that a lot of stress-strain relationships in a lot of materials are time dependent. Okay. meaning that, how you, not only is the magnitude of the loads that you apply relevant, but how quickly you apply them. And so, maybe you apply them, whether you apply your loads all at once, or maybe you apply the loads gradually, little bit by little bit. For a lot of materials, that's actually going to change what kind of deformation and what kind of strain that you obtain. Okay. All right. And so, remember we talked about on Monday that ANSYS has a feature which kind of, automatically slowly ramps up your load as a function of time. This is something that is kind of even more relevant for that. Okay. The main reason why, our stress strain relationships are time dependent is the fact that it takes time for a structure to respond to a load, right? And so when we run it as a simulation, it's something that we don't really think about because we basically see it happen instantaneously, right? So we have our structure, we apply our loads and constraints, we run the simulation, and the structure goes from its rest configuration to the deformed one immediately, right? But if you think about in reality, when you apply a load to a structure, it takes time for it to reach its final configuration, right? And so, kind of the most extreme case would be, maybe for like a, if you think of like taffy, right? Maybe that's not the best example, but if you've seen taffy, if you take a piece of taffy and you pull on it, you can be applying the same amount of force, and so the amount of force you're pulling it apart with is still the same, but it doesn't reach its final configuration right away. Like it takes time, like you're gonna be pulling it. And as you're pulling it, it's going to keep deforming like that. Okay. Most structures and most materials are like this, except not everything has the same time scale as taffy. So taffy is a little bit kind of different. So, question.
This is the material property, like the right side. Shows up, is that the input things?
Yeah, it's something that I think is more like if you have just a linear elasticity a material model, you don't really see it in the equations. It's kind of more of a kind of how quickly the deformations are applied. So it's definitely a higher order kind of effect. So linear elasticity is not going to capture this because according to linear elasticity, there's no time dependence there at all. And so you have stress, you have load, and you have deformation, and all that happens instantaneously. And so it's definitely for more kind of non-linear materials.
And when it's time dependent, does that also mean that it's position dependent?
Yes, it does. Yes, and especially for structure with large deformations. And so if you think of an extreme case, say you have like a cantilever beam and you apply a vertical load, as this beam starts to deform, then that load is going to be applied at a different angle because so let's say the beam kind of deformed along like this. If you're still applying the load in a vertical direction, that's going to be different than if you apply it perpendicular to that as well. So yeah, a lot of these are position dependent as well.
The reason I'm asking in terms of using time dependent stress or strain linear on non-isotropic materials, what are the effects of time dependent stress or strain when applied to those materials? Yeah,
so it's complex. And so those things, especially when you have kind of complex anisotropic materials, it can be complex and it's hard, that's why a lot of times you need a simulation to see, how those effects are going to happen. It's going to be different depending on the geometry, depending on the direction of the load. It kind of depends on all those things. Yeah. For a lot of materials though, you don't actually observe this because that time scale is very, very short. And so that's kind of the assumption that we've been making in our simulations. And so even though in reality, it would take your, let's say activity 3, it would take your signpost, it would take time for it to reach that final load configuration when you apply wind force on it. But a lot of times it happens so fast that that you don't really notice it. Okay. On the other side, so for more complex materials, you might have situations where it takes hours or days or even weeks to reach the final equilibrium state. So oftentimes we call this phenomenon creep, or the more trendy word for it now is viscoelasticity. Okay. Viscoelasticity is the idea that some materials, they don't behave exactly like a solid, but they don't behave exactly like a fluid, but it kind of has behaviors of kind of both. That's kind of a new kind of trendy thing to be researching right now. Is, reformulating some materials to be in this viscoelastic framework. So that's something kind of important to keep in mind. I would say, if you're working with kind of a standard metal or a standard kind of even like a standard plastic, this time scale is not going to be something that's particularly relevant. But if you are working with kind of complex materials, composite materials, anisotropic materials, it's something to consider. And when you're going to apply your loads, definitely you want to think about how many sub-steps or how many steps you want to use to ramp up the load to make sure that you get the final result. Okay. Okay. Any questions on this? Okay. So the last thing I want to talk about is the fact of kind of some of the assumptions that we make, in using these material models. Particularly the linear elastic material parameters. Okay? So I'm talking about things like the Young's modulus, like the Poisson's ratio, things like that. Okay. And so just like any kind of material property, for any kind of material, these are often determined through experimental measurements, and so through experimental tests. In particular, for the parameters for linear elasticity, those are determined through a test called a uniaxial tensile test. And so the way it works, and so let's say that you want to determine what the Young's modulus is for aluminum, right? And so what you would do is you would get a rod of aluminum. You'd stick it into a uniaxial tension test, and you'd start to pull on the material with some tension T, okay? And so what you would do is you would keep increasing the amount of load, and you would observe how much deformation that you would get, okay? And based on that relationship of the load versus the amount that the rod has stretched, that would give you values for the Young's modulus. And then if you measured how much the rod would kind of, get skinnier or to, then that would give you a Poisson's ratio as well. And then that Young's modulus, of course, is used as kind of a general parameter for stiffness of the entire material. Okay. Okay. And so doing this actually, we're using a lot of assumptions that, we may not have talked about before. Okay. So this assumes, or I should say, using this linear elastic parameter assumes that, first of all, it assumes that compressive behavior is symmetric to tensile behavior. In other words, whatever stiffness that you observed in tension, you're going to have that same stiffness or that same strength in compression as well. Okay. Another thing is that in shear, so when we talk about the shear modulus, that's computed using a deterministic formula. You may remember this formula from earlier in the class. So shear modulus is equal to E divided by 2 times 1 plus nu. Okay. And so just from that one stiffness parameter, we're also making assumptions on kind of a shear behavior as well. Okay. And one thing that we didn't talk about is that we have another property called the bulk modulus. And this is also computed based on the Young's modulus and the Poisson's ratio. So the bulk modulus is equal to E divided by 3, 1 minus 2. And so if you're curious, the bulk modulus expresses how resistant the material is to a reduction in volume. Okay. And so, of course, I'm bringing up these 3 assumptions, and there are more than this. This is just kind of three of the main ones, because not every material is going to follow this behavior, especially once you start to get into the realm of large deformations. And so generally speaking, if you have a situation where you have large deformations, and so deformations, what I consider to be large are deformations that are more than, I would say, more than 10% of the overall dimension of your part. Okay. And so if you have deformations that are larger than that, then you may want to consider different material models, maybe something like hyperelasticity. Okay. With that said, ANSYS does have a toggle, and so ANSYS does let you turn on what's called large deformation mode. And so we talked a little bit about that on Monday, But when you turn that on, it also kind of does a little bit for the material nonlinearities as well. Okay? So large deformations can help a little bit, but if you really have a situation with very, very large deformations, I would suggest maybe considering a hyperelastic. Okay? And so we'll talk about large deformation mode in our next activity when we come back from break. Actually, we'll talk about it mostly in activity 6 because we kind of skipped activity 5. So activity 5 we'll do after the break. In activity 6, we'll kind of get more into this nonlinear stuff. Okay. I think that's all I want to say about that. There's a little bit more about hyperelasticity in the notes if you're interested in reading about that. But we don't really dive into it that much in this class. So, I'd rather kind of spend the rest of the time today discussing your projects if you guys need help with that. All right, any final questions on material nonlinearities? Yes.
I'm not sure for modulus, but for the shear modulus, are you also assuming isotropic materials?
Yes. And so the question is for the shear modulus, if you're using this equation right here, you're assuming that the material is isotropic. Yeah. And so if you have an anisotropic material, and you found that and you have a different measure for the shear modulus, you can enter that manually for those ones. Yeah, typically, if you have the shear modulus, it's because you have data from a more complex material test. And so it's not just a uniaxial tensile test. Maybe you have a biaxial test, or maybe you have a compressive test as well, or a shear test as well. Yeah. Mm-hmm. All right, any other questions on this? Okay, all right, so that's all I wanted to talk about in terms of the lecture. And so, I'll stick around for the next 30 minutes. If you have questions on your project, now is kind of the best time to ask. I'll go ahead and help. There's a couple people in the classroom, so I'll see if they have questions first. But if you want me to look at something over Zoom, I'll come back to the Zoom call in a second. But if you're heading out, I want to say, hope you guys have a good spring break. It's been raining and cold and wet and stuff out there, so driving is pretty dangerous. And so if you're traveling over spring break, please be careful. Replace your windshield wipers. Get new tires if you need to. So last thing you want is an accident. I've seen a couple accidents actually already because of the weather. So I don't want that happening to you guys. So I want you guys to be safe. I want you guys to rest, recharge, because once we come back from the spring break, we'll be doing the final project and we have a lot of ANSYS activities to do. Okay. So hope you guys have a good spring break, and I'll see you back here in 12 days.
Thank you, Dr. Chan.
Yes.
It might sound.
This one.
Is it dimension based? Is it better which way the flow goes?
It does. And so you can see here that it's not symmetric on this side. And so it's not shown in this catch file, but there's like the plunger thing that goes down.
Yes.
So that's actually the valve mechanism.
I know. So it's like I don't understand.
Yeah.
But like my question is, does the water, if you unscrew the flange, does the water go up or go down?
Traditionally it goes up.
Just lower it up.
Yes. I think it can actually work both ways, actually.
I was like, I was confused. Like, it goes down.
Yeah,
I'm
yeah.
not sure which way to do it.
Yeah, that's a good question. I'm pretty sure it goes low to high, just kind of based on how I've seen these used before. But I want to say that it can actually work both ways too. But the stopper is mostly designed to plug flow in one direction. Once the valve closes, then part of what seals it is that it relies on the fluid pushing on that screen. So I want to say that it goes low to high. I want to say it pushes it up.
Yeah. And then for like for pressure, like one of my scenarios is how would it pressure?
Yeah.
Incoming flow. Like what I just use, is it safe to use hydrostatic pressure? Like with
Yeah, so the way that hydrostatic pressure works is actually interesting. So for this one, I would say just use regular pressure, because the way hydrostatic pressure works is that it adds kind of a height. And so, because if you have like a glass, like you have this right here. So the pressure in this water bottle is going to be much higher down here. And so the hydrostatic pressure kind of does that automatically for you. Like you have to tell it which direction is the height direction. Usually it's Z. And then what it'll do is that it'll vary the pressure according to gravity. So if gravity is usually 9.8. So if you set, I think usually you set the pressure at the bottommost, then it'll make the pressure, slightly less as you go. But because this globe valve is so small, I don't think the hydrostatic variations will be very small. And so I would just use regular pressure, just apply a uniform pressure.
And then for like in terms of the actual, say I'm assuming it's water.
Yeah.
Or hot water or say like what type of fluid I'm using and what are the actual mechanical properties of and where data.
Yes.
Like where I got the data from.
Yes, as long as it's not illegal. As long as you didn't steal it from a company or something like that, then yeah. If you did, then just don't tell me. Just I'll assume that it's true.
Yeah, because for the hydrostatic, I've been playing with it, but it's just like you have to make assumptions as you go. So it's like the more assumptions I'm making in terms of hydrostatic pressure, the more uncertainty it creates.
Yeah. That's
why I
why
wasn't really sure whether to use hydrostatic to show like a real life scenario, or just simply using pressure.
Yeah, I would just use pressure. There's less variables there. The hydrostatic pressure is mostly there for like, because people do like finite element simulation of like an entire dam. So it's for a dam that's like hundreds of feet tall, and the hydrostatic variations are huge. But for such a small device, I mean, you can see here that the entire length of the device is scale of centimeters. And so the hydrostatic variations are very small, even if this valve wasn't for
And for like our, we factor in the fact that this globe valve is small.
Sure.
Like because like assuming like for example like one of the scenarios I was thinking of doing is
okay. Yeah, you can do that too. I know
we
people
factor in the actual size of the valve.
You can. I know people have been doing situations where like something like an object strikes the valve from the side too.
Yeah.
And so of course for a smaller valve, it's less likely to happen. But you can do that. You can do that as well.
That was so I didn't want to say there.
Okay. Yeah, that's fine too. Yeah. That's. I think someone was doing like a golf cart, right? So, I mean, with the size, that would be. I mean, they have to drive the golf cart very precisely. You can do that. You can stretch reality a little, as long as it's not like as long as it's not like a whole punching or something like that. So as long as it's somewhat feasible. Okay, cool. Questions?
Pretty good.
Okay.
I think so far.
Okay. Yeah, if you have questions, just email me. All right. Zoom people, I'm back. Actually, let me stop the recording.